In this lecture, we explore one thing that makes Hdf useful for solving real-world problems: the ability to combine data and metadata into a single package which is self-describing. In other words, you can give an Hdf file to a colleague or a client, and they can immediately begin to make sense of what it contains without resorting to other sources of information. Generally speaking, data is not very useful all on its own. In order to make sense of data, we need to have other information that provides context. For example, consider a time series dataset stored in Hdf. In order to interpret this data, we have to know the time spacing between elements in the dataset, and we also have to know the absolute time at which the recording begins. Where should we record this information? The traditional way is to keep a notebook, either on paper or more commonly in the file on the computer, usually stored near the Hdf file that it describes. We can put in this notebook any information we think will be useful when we later analyze the data. This solution is very attractive because it's very simple. We don't have to worry about interacting with the file, adding a header, or defining our own format. However, it creates a number of challenges when we later analyze the data. For example, we need some way to retrieve the metadata that describes the particular data we're analyzing, which means we need to invent an indexing system. Every time we perform the analysis, we need to go back to the notebook and enter the information manually. And of course, if we share the data with someone, we also need to share the entire notebook. Here's an example. Suppose we have information stored in Hdf from a weather station. In order to make sense of this data, we need to know a number of pieces of information. For example, the name of the station, its location, the time spacing of the time series, the units of the time series, and of course, when the recording begins. This information could be recorded in a notebook. However, when we begin to have more stations, the problem quickly becomes overwhelming. Thankfully, Hdf provides a native mechanism to handle this problem. The Hdf solution is called attributes. Attributes are small pieces of information that come directly attached to groups and datasets inside an Hdf file. You can think of an attribute as a key-value pair, or like the entry in a Python dictionary. The key in this case is the name, which can be any string, and the values can be any type that Hdf can represent. Importantly, we have access to the full Hdf data type and data space machinery, which means that we can represent attributes that have any number of dimensions and any supported type. For example, the location here is stored as a 2-element array of type int32. It's important to remember that attributes are intended to convey small pieces of information that describe other objects in the file. If you find yourself creating very large attributes, or many attributes, you may consider using datasets instead. Keep in mind that when you read or write an attribute, you're required to read or write the entire attribute. They don't support partial I/O like an Hdf dataset. Let's see how we can access attributes from Python. In this example, we have a file representing weather information that comes with a dataset and a number of attributes already populated. We open the file, we retrieve the dataset, and to access the attributes, we use the .addrs property attached to the dataset object. The .addrs property returns an object that works very much like a Python dictionary. In this case, we have a number of attributes already in the file: the name of the station, its location as a 2-element array, the time units, and when the recording begins. Let's imagine that we wanted to add to this information the spacing between time elements in the series. To create a new attribute, we use the Python dictionary style syntax and simply assign a new value to a name. Here, we create a new attribute called time delta and give it the value 0.1. The dictionary metaphor is used for other operations. For example, to retrieve the value of the attribute, we provide its name, as we would when retrieving an element from a Python dictionary. We also have access to a number of other dictionary-style methods. For example, we can use the .keys method to return a list of all the attribute names. We can use the .values method to return a list of all the attribute values, and we can use the .items method to return a list of tuples containing the names and the values. In this way, we can treat attributes attached to an HDF5 object in a very Pythonic way. Unlike HDF5 datasets, it's very simple to overwrite an HDF5 attribute. Simply provide a new value and assign it to the same name in the attributes object, and the value will be updated. Finally, to delete an attribute, we use the standard Python dictionary syntax. Let's use Hdf View to examine the attributes in the file we just created. From the main Hdf View window, we can open the file, and on the left-hand side, we can see the dataset we created. If we right-click and do Show Properties, one of the tabs in the Properties window is the Attributes tab. Click on that, and we can see a listing of all the attributes attached to this object. For example, the location, which is a 2-element array of integer, the name of the station, a string, a time delta, a time start, and of course the time units. Here are some key things to keep in mind when using attributes. HDF5 attributes are the official way to associate metadata with HDF5 datasets. Try to avoid storing information in the file name or in other files near the HDF5 file. Instead, attach that information directly to the object in the HDF5 file that it describes. Finally, keep in mind that attributes are packaged up with the data and make it very easy to share self-describing files with colleagues or clients.